Contenido de Uninorte.co. No olvides suscribirte a nuestro canal.
Welcome to a new session of PiA Webinar Series. First, I want to remember that PiA is a cooperative initiative supported by Asociación Argentina de Cementología, SINSTAF from Mexico, Escuela Politécnica Nacional from Ecuador, Instituto Argentino de Oceanografía, Instituto Geofísico del Perú, Mississippi State University from United States, Universidad de la República from Uruguay, Universidad Federal do Espírito Santo from Brazil, Universidad del Norte from Colombia, Sequoia Scientific Inc. from the United States, and I'm pleased to announce that a new member just joined us, Universidad Técnica Federico Santamaría from Chile. I want also invite you to visit our webpage where you can find the past recording of the session of PiA Webinar Series, among other relevant information about sediments in the continent. Today we have invited us Paulo Gamaro with the talk Sediment Monitoring and New Technologies, Positive and Negative Aspects. Paulo Gamaro has a PhD in Water Resource and Environmental Sanity from the Universidad Estadual do Oeste do Paraná. He's a civil engineering from the Escola de Engenharia de Volta Redonda. He's expert in the use of acoustic Doppler current profiler in hydraulics and fluvial geomorphology studies, includes its application in the estimation of sediment load. He has participated in projects on the Madeira, Brazil, Mekong, Laos, Mississippi, United States rivers, among others. He participated in the design of the hydrometeorological network of the Itaipu Dam, one of the largest dams of the world, as well as in the supervision of its maintenance and operation, with an emphasis on supplying data for energy planning. Another standing remark is especially in acoustic Doppler methods, participating in the first tests in Brazil in 1993, and the first station to use horizontal acoustic Doppler methods in Latin America in 2001, author of a relevant book about the use of ADCP in current meters, participates in 2000 in the hydroacoustic group of UAGS, coordinator of Hydrometry Commission of Brazilian Association of World Resource since 2003, State Discharge Commission of World Meteorological Organization, Hydrology Commission of HICL, International Commission of Lardan, training course of acoustic Doppler current from Brazil, Paraguay ministries between 2004 and 2016, and he participated in the bigger discharge measure in a river in the Amazon River in 1994. So Paulo, thank you very much for being here. It's a pleasure to having you. So please go ahead with your talk.
Good afternoon, everybody. I would like to thank you for this chance to talk about a little my experience and to share what I've been practicing for more than 35 years. I expect that this follow what you would like me to share with the people, and I expect that all the people that listen and learn something and could go ahead in his experiments, measurements, and studies. Okay, let me start sharing my presentation. Let me see. A little bit problem. I always do that.
Don't worry, I will notice you when we can see.
I'm not finding my presentation right now.
Yeah, we can see your screen right now.
Yeah, you can. Okay,
Yeah,
let's do it.
now
Let's
disappear.
do it again. Yeah. You
Not yet. Remember, in the bottom panel there is a share button.
yeah, but okay. No, not sharing.
Now it's coming. Yeah, now we can see your screen, but not your PowerPoint presentation.
Why don't?
No, now you close it. You have to open again and put it in
Okay.
presentation mode.
We'll share. But I can see my presentation here.
No, but you have to share your screen first.
Okay. You see now?
Yeah. Now, yeah, and go to the presentation mode. Yeah.
Okay.
Yeah, it's okay.
I hope. You see?
Yeah. Go to the presentation mode. Yeah. No, 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 no.
What's happening?
Yeah, it's okay right now.
I'm not seeing you and anybody.
Yeah,
Even
no
me,
problem.
I can see.
Yeah.
Okay, no problem.
Yeah, I would let you
Okay.
know if something happened, but go ahead, please.
Okay. So what I bring today is about sediment monitoring and new technologies, positive and negative aspects. Why I choose this is because we are in a world that every moment, every single day, we have a new technology in everything, especially we can see this in our cell phones. Every day we have something new. And you have to deal with this new technology. We have to learn this new technology. We can see this in our cell phones. So I remember when the first time I have a cell phone is just for calling someone. And now our cell phones are like a computer. We can do a lot of things with this. It's the same thing with the technology that's arriving for measurements, water measurements, discharge measurements, sediment measurements, and a lot of other things of subjects. So right now we can see better now. So the concepts and principles that rules our old technique should be revised under new vision. Why is that? Because now we are seeing better. We can see things that we couldn't see before with the old technology. And also we have to find out the limits of the new technology. And these limits should be established. So we cannot go thinking in this same old thing. That is an old wisdom. I took this from Bible, so it's very old, but it's very it's very real for now. That said that no one puts new wine into old wineskin, or else the new wine will burst the wineskin and be spilled, and the wineskin will be ruined. But the new wine must be put into a new wineskin, and both will be preserved. In Luke 5:37-38. Why I put this? Because if we going to use the old techniques and use the new techniques with the old things, the old rules, we probably is not enough for us to understand and to use. It's like I have a cannon, I have a powerful weapon, but I don't know how to use it. I just know how to throw stones. So we have to start seeing a revision of the old techniques. We have to see how we do. When I say old techniques, I'm not telling is completely unactualized, but I mean it's old because there is new one. It doesn't mean that's not good enough. Again, it's still good for the use we used to do in the past. But when we have new techniques, this became old. Okay. So here we're some samplers for bottom. We have to come back. Why we collect sediment data? First of all, the sediment reduce storage capacity of reservoirs, and we are seeing this many times. These are increasing in our world. Why is that? Because the human being is changing the environment, and the sediment is going faster and faster to the river, to the water bodies, and so it is reducing or even completely turn the reservoir unusable. Also, the sediment causes changes in channel configuration, slowing or halting either temporarily or permanently plant growth when deposited on productive land. So, and right now, when we are seeing that the population of the world are growing and growing, we need more and more plant growing and yields and things like that. And the sediment could ruin this in a long term. We also have navigation problem here where I live. I live in the confluence of Paraná River and Iguaçu River in the south of Brazil and border with Paraguay and Argentina. We can see a lot of yield of soy, corn, wheat, transportation, and this transportation comes by the river. Also in Paraguay, most of the transportation comes by Paraguay River. So, and when we can see a lot of problems there, problems like this, sedimentation in the middle of the river where the barge couldn't pass by, the barge couldn't have to stop, and we can lose millions of US dollars every day. This is Paraná River, and we can see right now that we have 1 feet of water and sandbars, and this is just a small channel where we can go with the boats. So what do we need to have sediment data? We need to understand. We have to have this data to understand how it works. First of all, the time distribution of sediment concentration and transport rate in a stream. We have to evaluate the sediment yields. We have to evaluate the erosion and deposition in channel systems, like this one that I just showed you. The amount of size characteristics of sediment delivered to a body of water. These are what I'm telling when we are, the human being are changing the plants and everything like this. We are changing the characteristics of the sediment as are going to water body. We also have to understand the relationship between sediment, water quality, and biota. The characteristics of sediment deposited as related to particle size and flow condition. This is something very common to understand. Everyone that works with sediment knows these items that I just told you. So we have to monitor continuously. And to monitor continuously, it's completely impossible to have measurements every day, every moment, because of time. because of the money that we spend to do this. So we used to use the computation of a transport curve or sediment curve, and continue. So we have to monitor it continuously the daily in daily discharge basis of the sediment. So here an example of water hydrograph of a water and the sediment curve here. So let's see a little bit more about regular and conventional method difficulties. Just right here, we can see that people here is measuring. We have a sandbar that is about 1 feet of water around here, and the boat couldn't approach the guy, and the guy is measuring all the sandbar. This is in the middle of Paraná River, just upstream the Itaipu Reservoir. So let's see the difficulties to collect regular sediment data. We need to have a representative sample, and this requires me to selection a good site and understand the characteristics of the place. We have to understand the temporal variability, the spatial variability, and sampling frequency. So I'll show you some site characteristics about depth, which would be a problem to collect sediment. Of course, this is a very unusual place, is in Amazon River in Taquatiara station. We can see the depth is about 100 meters, and we have a lot of turbulence in the bottom that could allow me the equipment to measure well. So in this case, it's a very big problem to collect sediment along with the old mechanical meters. The width of it is also, we have about 2.5 kilometers wide. It's a very complicated situation for our measurements. And this is not only Amazon River, but all Amazon basin. We have to face this to collect regular sediment data. Even in Paraná basin, we have this kind of problem, Paraná and some of his tributaries. High water velocities, we can face high water velocities about 2.5 meters per second. So when we are descending our mechanical meter, we will have problems with this, especially in these high velocities. These high velocities are not only usual for Amazon basin. We can find this water velocity, high velocities in Paraná River, in Iguaçu River, and in Paraguay River in some condition, in flood condition or semi-flood conditions. The other problem we have to collect sediment data is the access to station, especially in the Amazon basin. We have to face the forest. We have to navigate for days to arrive some stations. Other problems is in the Andean rivers, we have problems also. And I mean, this is the one very problem, but we have more problems with access. So what we have to collect is a representative sample. So a characteristic of the sample that is proportional to its occurrence in the local environment at the time of collection. It means that every sample that I collect, it should be proportional to the place where I'm measuring. A representative suspended sediment sample will have a sediment concentration and size distribution equal or similar to that averaged over the stream cross-section when the sample was collected. It looks simple just to do this, but when you go to the field, some places are very unusual, very complicated to have a representative sample. Here is a very known picture of about different diameter of the sediment and how it's occurred in the rivers, silts and fine sand, very fine sand, medium sand, and everything. It's very known. We also have to this that some distribution of silts enclave, or I mean fine sediment. We have the measurements in the surface doesn't differ much from mean of the vertical. If we divide the concentration, the mean concentration of the vertical between against the concentration of the point, it should be around 1. How much closer than 1, the better it is. So you can see that for finer sediments, it's not difficult. I mean, it's not difficult in a 5 feet depth, but the things start to be completely different when we have a coarser sediment like sands and fine sands and so on. In the surface, we see here the concentration, and we have here the mean concentrations in the vertical. We can see that we have the quotient. It's about 5, 4, 1.5, 1.4, 1.7. It means that it's not enough for us to just collect in the surface of the water. What does this mean? This means that we also have in many stations that we go every 3 months or every 4 months to measure a completely measurement of sediment. During this time, we have someone that goes and collect the surface sample for measuring sediments. In rivers with coarser sediment, with sand sediment, this is a big problem, a big error. We have big errors. And here, I don't know the rest of the South America, but in Brazil and also in Paraguay, in Uruguay and Argentina also, we have a lot of rivers with a lot of sand. So it's a problem to have to measure it more frequently, and this is not every time. It's not possible. So we also have to see the relation among the suspended sediment and concentration. The relation with the depth, a turbulence maintains sediment in suspension. Fine sediment tend to be uniformly distributed in the water column. The concentration of coarse sediment may increase with depth, Stokes' law. It's okay, we can see this, but this is not very easily to understand in big rivers like in the Amazon basin, in the Paraná basin, and things like that. The width sediments may be non-uniformly distributed in the cross section. This may be due to incomplete mixing, inadequate time of mix, weak turbulence, density gradient, weak, and everything like that. We also have to understand the reason, the relation with the season, the flow history, the man's work, the changing of the environment around our section. We can see some mechanical samples. Here is one of the river of the Amazon basin, the Madeira River, one of the most, they carry most of the sediment in the Amazon basin. And we can see more samplers, and we can see that we have some boats not adequate for these measurements in a low flow, low discharge. It's not possible to measure with this kind of boat in high discharge. The other problem is when we are in the middle of the measurement, we are just anchored your boat, we start to measure, and some soy barge coming, and you have to move very quickly to not be hit by this barge. Or a ship in Amazon is very common for us to big ships cross the river during the measurements and things like this. From here you can see we are in the boat, measuring, and we have the ship just passing very close. And you know that if you are in front of it, they will not change his route. We have to change and very quickly. So you have to pick up all the instruments, bring it to the boat, and go as fast as you can from out of his front. So problems. Wide River sample may be not representative. I mean, Wide River. When I mean Wide River, I'm talking about more than 2 kilometers wide. I give an example in the Solomons River. It's one of the tributaries of the Amazon. The width is about 3 kilometers and 200 meters. So if I used to collect 10 verticals, I have one vertical each every 20 meters, at 320 meters. And of course, this is not representative because they are completely different environments measuring, but they are representing at least 640 meters, 320 meters from one side and 320 meters for the other side. So this point in the middle of this should represent all this area, and this may not be representative. Again, we can see a big boat for Amazon River measuring, and we can see a ship crossing the cross section. We have a problem with measurements. Like we do not measure as much as we need, especially in South America. I don't know much about Colombia. I don't know much about Venezuela and Peru, but I know about Brazil, Paraguay, and Argentina, and even Uruguay. We're not measuring because we have problem with budget. We have low budgets for this. We have few technicians, few teams to go measuring all the rivers, and we also have locomotion difficulties. We sometimes take many days to arrive to one station, especially in the north of Brazil. But I go and I go for to see what's happening in the United States. This is a 2012 graph, and we have here the daily stream gauge, and we have here the daily sediment gauge and how it decreased in 2010, if I'm not 2012. So even in the United States, we are decreasing the collection of data of sediment. I also bring here a sedimentary stations in Brazil and a plan of ideal number. We can see this green, the dark green here is the operation sediment station, and the light green, we have a proposal to ampliate the sediment stations. As I'm talk a lot about Amazon and the north of Brazil rivers, because they are bigger and they are what we need more data. I bring this map showing the sediment station in Amazon scene, and it's not enough. We not measure regularly. What I mean regularly? Regularly, it means that I would like to see my network being measured every, let's say, once every two months, but that's not true. We have a lot of difficult assets. I already talked about this. We have here is the Manaus, the capital of Amazon state, and to arrive and measure in these stations, we can take about 10, 20 days. It depends on the river are in floods or not, navigating to arrive here. So it's a big problem. Then new technology arrives and you say, wow, my problems are solved. I not have to have any problem with mechanical meters. I don't have to have any problems with my sediment collection data. So can we relate surrogate parameters to sediment? Promising techniques, backscatter from acoustic velocity meters, laser diffraction, turbidity may work well when sediment flow relationship is poor. When my curve of sediment, my curve is not good enough because I don't have a lot of measurement, these techniques could work better. But this is the question, very important. Do we really understand that new technology bring new concepts to add to old ones? It's not straightforward measure and have sediment suspension concentration. I can just see my equipment and say, oh, we have this concentration or we have that concentration. We have to calculate, we have to work in the data to get the concentration. And also, we know the limitation of this new equipment. We only know the limitation measuring and measuring and measuring. And we've been measuring with all of these equipments here, but we still have to understand more and more about the limitations. And also, we doesn't only have to have the knowledge of the limitation, but this limitation should be spread out for all these technicians that work with it. They should be very right and spread out for them to know to use the technology correctly. So to sediment data, I have to have water discharge. We use the current meters. Now we can use ADCPs. For the particle size analysis, we have to samplers and sediment concentration. We have samplers. Now we can use in connection with ADCP, with lists, or with turbidimeters. But we still have to measure. So at first moment, when we just settle down a little bit, we settle a little bit and see what we have, we see that we can acquire more data. Yes, we can, especially ADCPs, because we are having a lot of measurements in the whole world, much more. It's becoming more easily to buy an equipment, an ADCP, and so we can acquire more data. But could be not so precise. I'll show you in advance. But in countries with low budget, small numbers of teams, many different river size, especially if they are large rivers, this could be a very good thing. How is that? If I every discharge measurement, I use the ADCP. I'm talking now about the ADCP because this is we use more. I can at least have the idea of how much sediment we have, how much the sediment is changing. I'll show you that in advance. But I still have to spend more time, money, to train our teams with the new techniques and teach them how to acquire and calculate data, how to acquire in the field, and how to transform this data in information, in sediment information. I still have to run measurements with mechanical meters. Less is true, but I still have, because I have to establish a correlation between mechanical meters, concentrations measured with mechanical meters, and one of the equipment that I just show you. So let's see a little bit about the new surrogate meters. We have here the Madeira River and some measurements with sediment measurements and measurements with EDCP. So the surrogate technologies for suspend sediment are this one. There's the bulk optics, attenuation, scattering, multi-frequency optics, laser diffraction, digital photo optic imaging, pressure difference, gamma attenuation, acoustic, etc. But I'm not going to talk about all of them. I only will talk about bulk optics attenuations, which means turbidimeters or optical. Laser diffraction, acoustic backscatter, because is the technology that we are using more and more. Let's talk about a little bit about the turbidimeters. The definition of turbidity, an expression of optical properties of a liquid that cause light rays to be scattered and absorbed rather than transmitted in straight lines through a sample. We have one here. And what are the factors affecting measurements? And these factors, we have to take care with them when we establish a station to use these turbidimeters. The particles, the color, the light source, particle settling, mechanical sample problems, numbers and configuration of the detectors. And we also have to understand the turbidity limitation. Each regression model is site-specific. I can use one instrument to one site, establish a correlation with concentration, sediment, and suspension, and take this instrument to another site and use the same regression. This is not possible. We have to start all over again. Turbidity values from different sensors are not equivalent. We have a lot of turbidity from different manufacturers, and they are not measuring the same values from the same place at the same time. If we put 1, 2, 3 together, they are different. This is because if I use one of this turbidity and use another turbidity in another place, the regression are completely different. But if I stay this turbidity in the same place, in the same station, and establish a correlation, I can use it if it's a good place. Truncate turbidity at the high end of a loose, I mean, very high turbidity, we have some problems. Here's one of the first analysis. It's back to April 1999 from Bo Buchanan, from USGS in San Francisco Delta Bay. And this is the correlation between the suspended sediment concentration and the turbidity. We can see it's a very good one. So we can use it just reading the turbidity to find out the concentration. The problem where I am collecting data, because I have seen in some places that people are putting their equipment in one side of the river like this, and thinking that the correlation for the whole river will be okay. This is not good. Also, the USGS says that when you are measuring with mechanical meters, samplers for sediment, we also have to put your turbidimeter in each one of the verticals to establish the correlation. So this is what the people from USGS find out about book option notable. The positive thing is they're very cheap. It's a relative mature technology. It's most common surrogate technology. We find a lot of them. We have a concentration at a point, and we have contact with this equipment. The negative thing is that it's small operational branch, so I cannot use one of these in a river like Paraná River because I measured just a point in a river with width about 1 kilometer. It's not possible. It's prone to falling. We have to be with high maintenance looking for this if it's not to clean up the instrument every since and then. Laser diffraction. We have here some back to 2002 some tests used by the USGS, the Gray, John Gray, and we can see the instruments here and here. It was placed in Colorado River about topping, and they used to establish correlation there, and we can see here the results of it. It's, I mean, I would say it's a good correlation. And also we have the list, SL that we can use in every vertical, which can give us particle size distribution concentration at the point of contact. Positive thing is the particle size distribution concentration is proven in marine. We also now, it's back to 2010 or something. It's been proven in river, we can see in advance. And list SL will be isokinetic. Negative is the operation range is a function of the particle size distribution and could be limited. I saw one problem here in Madeira River. We have a very, very high concentration and then was clogged. But it's a place very complicated to measure. Might fool in remote use mode. And about the price, I don't know if the price is still this. I probably shouldn't be, but it's still a little bit expensive. Here is experience in 2011 in Illinois, and we can see the results here. The purple sample, the samples with mechanical meters and with the list in one single vertical and flows. And this is a summary. They did a good range of testing, volumetric concentration issues, software revisions. It was back there. I know that they already changed it. And percent finer than 2 micron. Overall good list SL performance. So now I'm going to talk more what I have a good experience about acoustic backscatter. Well, the first study is about using ultrasonic for suspended sediment, come back to 1962. You can see here Gordon Fleming. And we also have a lot of studies in 1994, Reich and Nashville, and also in Colorado River in Kenya, using multi-frequency acoustic system about topping, right, and all. The implication: increased accuracy, greater resolution, less sampling needed, immediate information. This is a thing that we can think using acoustic backscatter to estimate suspended sediment concentration. Has been in practice for more than 20 years. Acoustic double current profiler measure backscatter, or the strength of the reflected signal from particle in suspension. The magnitude of backscatter depends on ADSP frequency and suspended sediment concentration and size of the particle. So I show some important aspect. I'm not going very deep in the technique because we don't have time for this, but I can show you some things and some occurrence, especially in the Amazon basin, where we will just use would be more, will help more us. So important that the signal correction or the intensity of the loss. We have been spreading, water absorption, sediment absorption. This is the equation. So when our ADCP gives the intensity of the signal, he is going down because of this loss of absorption, water absorption, sediment absorption. It goes decreasing the intensity. Using this equation, we can get the backscatter here. This figure is just for practical understanding. It's not is really a correction with this equation here, but to understand the difference, we can see it because one of those measurements is measuring counts. Counts is one measure for very, very high values measured by the ADCP or very, very low values ADCP. You can transform it in decibels, so you can use the equations to find out the sediment concentration. So I put a resume what we have to do, acoustic data processing. We collect raw backscatter in multiple cells. We subtract the noise and convert to decibels, just what I said right there. We calculate near field. Near field is because just close to the equipment, the spreading of the signal is not the same the rest of the vertical or the profile. Why is that? Because the function of the instrument. And so we have to calculate the attenuation of the signal, what I just show you about the attenuation by water and attenuation by sediment. And we correct for absorption by sediment, just what I told you right now. And you calculate the average backscatter and relate it to a sample data. Which is the sample data? Sample data is the data from mechanical meters. So here is in 2012 a working group for evaluate some new technologies of the USGS and open to other scientists. The advantage is high temporal resolution if the equipment is fixed. High spatial resolution if it's mobile, if you are crossing the river with an equipment. Improved accuracy and reduced cost. Concurrent velocity measurements with discharge. If I measure discharge, I can also use for sediment. Highly robust in environment. Ubiquitous in stream flow monitoring. Large sample volume. Multi-frequency may indicate sediment size. Disadvantage, complexity of the signal processing. What I just told you, we have a lot of calculations to process the signal we receive and transform it in concentration, in suspended sediment concentration. Variety of signal processing among manufacturers, I'll show you just in a moment. Inconsistent data by different instruments from different signal processing and different frequencies and different size of the cell. Low concentration limits to technical frequencies. So many differences in instrument deployment, signal processing. We have multi-frequencies from 0.5 to 25 megahertz. Broadband, narrowband, profiling, non-profiling, fixed installation, continuous monitoring of fluvial sediment. So we have here the fixed installation in the bed of the river, fixed installation in the bank of the river. And we have all these measurements for wave currents, bed forms, suspension, everything like this. We have to deal with this to find out which is the best one for our stations, for our rivers, and then use it. Well, so let's start see a little bit about some experience, side look experience. I mean, a fixed instrument. We have one, a 500 kilohertz SL from Sontec here. It was used in Itaipu Reservoir to give discharge and some data of sediment. We also have here some a DVM or Excel side-looking experience from Mollywood in Idaho, in the Snake River and Clearwater River. The range in sediment suspension concentration 3 to 210, in the Snake River 7 to 389. Average percent of fine 62% and to 64%. Average of percent of organic matter, that 10% at high suspended concentration and 26% at low suspended concentration. In Snake River, 4% at high suspended concentration, 17 at low. Well mixed, no. We have some results here. We can see data from concentrations and in Clearwater, and in Clearwater is this gray squares, and Snake River is this brown, and we can see with our square to 0.85 to, and not so good in Clearwater, about 0.55. This is using discharge as a surrogate for sediment. I mean, using the curve, the concentration curve or sediment curve for establishing data. Using acoustic surrogate, we can see that a lot more better. In Clearwater that we find here 0.55, we found here 0.92, and Snake River, which about with discharge or flow through as surrogate, we have 0.86, and for acoustics we have 0.92 R2. So very good results. So the results of a lot of measurements, a lot of instruments using to surrogate sediment. The best one was acoustic backscatter with 300 megahertz. In clear waters. In Snake results, the better was 1.5 megahertz acoustic backscatter for side-looking equipment. Here we have a graph that we can see this a little bit. The blue one is stream flow. We have a stream flow transport. And we have with 1.5 instrument transforming in suspension concentration. As a summary of this experiment, we have acoustic is the best surrogate technology. Higher frequency work best. We saw the 3.0 megahertz. And we see the R2 is 0.92 for both sides. Low antennas. We have the data about every 15 minutes. Total fine and coarse fractions. We work in both of them. Improve the overuse of flow along over short and long time scales. The improvement is when we are improving our correlation. Well, right now I want to bring you to visit the Amazon basin, going where we do have problems. And we do have problems not only with acoustics, turbidimeter, or lists, laser diffraction. We have problems with mechanical meters because all here are huge. We have huge rivers. We have a lot of mass of water flowing. We have high velocities, very high velocities. I brought you here just a measurement. This is in Amazon River mouth. It's not real mouth. It's about 40 kilometers from the mouth of the ocean, Atlantic Ocean. But we can see the velocities here, and the whole section has about 12 kilometers and take us about 3 hours to cross the whole section. But we have here the average backscattering decibels, and we can already have a qualitative data of sediments. We can find out where we have less sediment, more sediment, and so on. We also can have here, we can see these points here, is because we are using echographic echobatimeter using, and they interfere with his sound, with the measurements with the ADCP. This could be a problem, yes, it could be a problem, not for discharge, but for sediment, it could be a very big problem. We also have waters meeting. This is a very known place where the Solimões River, with a lot of sediment coming from Andean, and the Negro River with a lot of organic matter, almost nothing of sediment. This goes for about 150 kilometers without mixing this water. So if you have to measure here, we have problems. We can see here is the backscatter of the equipment. This is the Solimões River, exactly what we saw here, and the Negro River, a lot of sediments and almost nothing of sediment. So if I use the acoustic Doppler for discharge, I would have to split in two to use it. It's a big problem to using mechanical meters because of the depth I showed you before, and that's high waters in some seasons of the year. I also want to introduce you the Madeira River, one of the carriers to the ocean, most of the sediment of the Amazon basin. Here we can see about in low waters, 4,400 cubic meters per second, very low waters. And we see that the intensity is just coming down very normally. But we can see with the backscatter in the whole section that we have a lot of reflections here. So qualitative data, I already can tell you where I should put my mechanical meter, although we have 37 meters depth. I also same place, same river. Now we have 20,200 cubic meters per second, and we can see that the intensity of the signal is going down very, very fast. We have a lot of loss here because we have a lot of sediments, and when we transform this intensity in counts to a backscatter, a corrected backscatter, we can see that we have things not usual here. We have some kind of let's see, sediment, unusual, that put very down in decibels this profile. And we go further. Now we are all the measurements before, we are using the 600 kilohertz ADCP, but right now we are measuring 47,500 cubic meters per second, and the 600 couldn't measure anymore because there is so high concentration that the signal couldn't go to the bed of the river. So and we can measure with the 600. We have to use a 300, and sometimes in past we already have to use another frequency because 300 couldn't reach the bed of the river also. So we can see now that we have when the sound touch solid, the count is 225, and it starts about 205 or something, and very quickly it goes to 178, and then go about 160 here. And we can see that backscatter here, we have some loss, very high loss here, because the instrument could be a noise, and then very quickly the backscatter goes down. So we can see from this data that we have most of the sediment in the up to 8 meters at close to the surface, not in the bottom. Yeah, and we can see here why. This is the velocities, and we can see that it's around 8 meters. So probably that's why we have a lot of sediment, fine sediment. Right now we're going to another station in Amazon River. Óbidos is a station in the middle of the Brazilian Amazon River, from the entrance of the Brazilian territory to the ocean. This is a very important station, and we are measuring about 203,500 cubic meter per second using 600 kilohertz, and we can see that 600 could reach the bottom of the river, so there is not much sediment here, probably because a lot of water. But what we can see here is that is a lot of turbulence in this area. There is so high turbulence that we have a decorrelation, and the signal couldn't for discharge. The signal couldn't be read by the equipment. So, but well, I could not measure with mechanical samplers here because of the depth, about 68 meters. But also I will have problems to measure with mechanical or ADCP measurements here. What I'm trying to tell you is that the Amazon Basin is a very specific place, and a good specific place to make researches and how to use these instruments. Probably the other place like this would be in China, in the Yellow River, or the others in China with a lot of sediment and things like that. I'll show you, the Purus River is one of the Amazon tributaries, and we made a measurement in Beruri Purus. It's a station, and the station is not very deep. This is not a very large river. It's 27 meters deep. There we don't have higher velocity. The velocity is about 1.4, 1.5 meters per second. Not high for Amazon standards, and we can see that we are about the discharge of 10,350 and 350 cubic meter per second, measured with 600 kilohertz, and we can see the intensity here. It's not a sediment attenuation. It's probably some noise from the boat, the instrument. is collecting. But we can see it goes from about 120 to 90 something. That's not a problem. What is strange here is when we uh, you put the equation of the loss in this intensity, we can see that the profile it's go stronger as it is going to the bottom of the river. Probably much sand, but at that time it wasn't. We were using the mechanical meters and we didn't find sand. Now we have the Purus with 28,560 cubic meters per second and 600 kilohertz. And we can see that now we have a very, very high declination of the intensity of the signal in the beginning 8 meters deep, and then it goes down normally. But the same thing happens when we go and we process data for backscatter, and we see that they go slowly stronger as we approach the bottom of the river. And we can see here is a average backscatter of the whole cross section. We can see that we have a lot of sediment in the bottom of the river, a lot of reflections. That means a lot of sediment, probably in this case sand. So when we establish this graph between discharge and suspended sediment concentration, we can see that there is not usual to see the discharge going up and the sediment going down. And the same thing we can see here. And why is that? When we establish a correlation, the correlation is not good. We can see the R2 is about 0.6. And why is that? It's because one of the things that we have to take care when we process data with acoustics is the viscous and diffraction loss. So, it's in Portuguese here. There is a relation between the particle diameter and concentration and the size of the acoustic pulse. What means that different results for sands and for silts and clay. And this is a graph that we have a viscous loss region in milligrams and changing with the return of the signal in decibels per meter, and the scattering loss region is a diffraction region when the instrument the instrument reads the sediment with more coarser. So this is what's happening here. That's what we call the acoustic sensitivity between the relative sensitivity. It grows until 1, it depending of the size of the particle. And we can see this in this data collected in this place. The viscous loss are much greater than loss by dispersion, by diffraction here. And every month we can see this. And the other thing that we can see the signal is not coherent with the concentration, sediment suspended concentration. We can see right here in February that the absolute backscatter about 75, and the suspended sediment about 159 milligram per liter. And here in March, almost the same, and we have the concentration about almost half of it. This river is very complicated because they have influence of the other rivers, and the other rivers put some different diameters of the particles and mix it, and it's very complicated to establish a relation between acoustic backscatter and sediment concentration. I also want to show you, I don't know how my time is it, but I'm almost finishing. I have to show you a study from Wood, Zupiani, Landers, and others in Missouri River about using a multi-frequency down-looking ADCP. Why a multi-frequency? Because only we can establish a particle size with only one frequency. We need at least two frequencies, and crossing each other, we can find out the particle size and much better for establish a correlation. This study was done in Missouri River, and we can see for a 1200 kilohertz ADCPs and a 600 kilohertz ADCP, the regression between the loss and the concentration in some points of the Missouri River. Always, all of them have R2, a very good R2. We can find here 0.887, 0.93, 0.87, 0.89, and also here with the regression with the 600. So both of them are working better. As I said before, the higher frequencies respond better than lower frequencies. As we see here, R2 has 0.61, 0.7, 0.56, 0.6. We can see here. Conclusions of this study: strong correlation acoustic intensity against suspended sand concentration. Similar results for both frequencies, despite the R2 is a little higher for 1200 kilohertz. 5, the sediment depreciable in presence of sand in suspension. What I mean is we are not have to worry about the fine sediment interfering here. I mean, we don't have to worry about the loss, the viscous loss for this study. Effect of part size variation. So we can see a little bit about this, but not enough to have a problem. And there is no noise between the 1200 kilohertz. I'm already finishing. So relevant results for Big River: high spatial resolution, low field costs and lab, low danger in measurements, in high water measurements, we can use that. And the last one is this study of the granulometry influence in the Paraná River with Lopes, Weisbel, Zupiani, Latozin, Cetonins. And we can see here the results with 1200 kilohertz and 600 kilohertz, high R2s. So the conclusions for the whole presentation: each technology has its own limitation, but we have to test it in every place we are using it, we are going to use it. So not every place is good for all technologies. That's, of course, easily to understand. Technology is opening new horizons to better studies and understanding nature. Acoustic has advantage to have a high spatial resolution. ADCP are used frequently to obtain discharge data, so at least we can have a qualitative data of sediment. So thank you for your time. I hope I could give you some visual of this thing, especially in big rivers. So questions?
Oh, Paulo,
Yeah.
thank you. Thank you for this survey of the measuring techniques. Very interesting. We have time for a couple of questions. We have one from Philippe Raton. Could you talk a little bit about the ADCP potential to estimate bed load sediment transport, especially considering the bottom tracking feature and the dune tracking approach?
Okay. Hi, Philip. How are you? Well, I've been using some places in Paraná River the use of the ADCP for bed load estimate. We have a little problem about this, that when we the signal approach the bed, there is some noise there, and we have to take care with this noise to read correctly the data from the bed load. For dunes, I have used it in Paraná River, 3 or 4 stations, tracking dunes with ADCPs, and we have a very good results. I can give you these details if you send me an email. I can write here an email. Okay, the next one is. Oh, yes, George Marino. George, you can use without sampling. You have to establish a correlation between the mechanical sampling for acoustic. It's not possible without it right now. Maybe in the future, I don't know. We need different equipment, but not now with ADCPs. To Guillermo Restrepo Torres, when there are large amounts of suspended solids, this accumulation affects the highs that are generated downstream in slaughtered weir. What type? What type of monitoring technology used in this case? Well, I would say it depends of the how large is your river. You can use. I think you can use any of this if the river is not very wide and not very deep. You can use turbidimeters, or you can use the least, or even the acoustic Doppler, fixed acoustic Doppler. Any one of them. It's just you have to take care to use the correct technique. Pedoc, thanks, Paulo, for a very interesting talk. You showed a case where the highest concentration were found close to the water surface. Oh, yes. I found this two times. One of this is in this case of the Purus River. It's very strange. And I just went there for one time and I measured at that time, and the others I used data from others researchers. So I could not tell you why this happened. The other place I find it was in Negro River, and about let me think, about 8 or 10 meters, we have a column of organic matter in the whole cross section, interfering with the acoustic data. And there's not all the time, but sometimes of the year you can find. I can give you the data if you want to show it. It's you're right. It's a very strange thing, but I found it 2 times.
We have another one from Yogi Agrawal.
Did you take samples to confirm this and discard other explanation? For example, the presence of air bubble close to the surface. Yes, we use sample at that time, but I didn't saw. Actually, I didn't look for bubbles at that moment. What I found out, it's sometimes we have noise from the boat, noise from the equipment in the boat that interfere with the data and could be wrongly understand like a high sediment. We have to take care of this. Okay, that's all. Okay.
No, we have in the bottom of the panel a question from Yogi Agrawal.
Hi, Yogi. How are you? Thank you for the chance to talk here. This 600 and 1200 kilohertz frequency is scattered in highly regime. So the calibration change with the particle size. Can you compensate to get good concentration? Well, I would say that I would use both equipment. I would use the list and the ADCP together. So this would give us a much better scene of what is happening in the section. The problem is that the price of the equipments, and we maybe here in South America we can afford to have both of the equipment with enough numbers to measure in many rivers. I don't know if I answer your question, but I think this would be. You are right. The using Harari mode when it's out of this is completely complicated.
Okay. I have a final question from my own. Okay.
Okay.
Do you work closely with Itaipu Dam designing a very well a dense hydrometeorological system for taking decisions, and I guess that this monitoring system was really expensive, you know? What do you think is most worth, the system or the lack of the system to make decisions about the control of water, the control of sediment, the functioning of the dam? I am asking that because many times our government or institutions say that the monitoring and the equipment, you also say, is too much expensive and they have to use the old system or not too much then monitoring network.
Okay, I can tell you that without doubt that Itaipu has the best network for this water approaching to his dam. We measure every month, not all the stations. We have about 60 stations, and in the whole basin that approach just down the dam before or upstream the river that is in state of São Paulo, and we measure. We also have acoustics Doppler measuring in the entrance of the reservoir and a little bit upstream of the reservoir, and this is for energetic studies to predict how much water is coming, and this. Sediment is another matter. Sediment was not with me at that time. It's another section. I don't know why they established that in the beginning of the Itaipu. And sediment is a problem, I think, to monitor it, especially in the basin of Itaipu and others. We don't have much. What I think is that we have to develop more and more this surrogate methods to have a better understanding what's going on and what is monitoring, and the frequency of monitoring should be better. As I said before, we don't have the whole thing is we don't have money enough for this. Itaipu is a little bit different because Itaipu has money because it's a high production, and most of the energy of Brazil comes from Itaipu, so they have money for this and can afford to measure every month, and so we are calibrating the index velocities and also the stage discharge sections. But sediment is different. We also have problems because we have a lot of dunes approaching to the reservoir. So as I answered to before, we used to calculate the bad sediment, the dunes, with ADCPs and not only ADCPs. We use the ADCPs to measure the dunes displacement and how much of these bad forms are arriving into the reservoir. But we don't measure with mechanical samplers since 1995. We are measuring with turbidimeters. When we see I still using, I'm not in Itaipu anymore since 2016, but I never measured sediment until 1995. I made the last measurement with mechanical meters in the Itaipu Basin. Since then, they developed some studies. I can tell about the studies. I don't know there, but I know that they are using turbidimeters for this monitoring sediment in suspension arriving in the Itaipu reservoir. I don't know if I answer your question.
Yeah,
but
yeah, and that gives me another idea for another question. You are very familiar with the situation with the monitoring in Brazil, for example. And if we want to take Brazil as an example in Latin America, and if we had a steady funding for make a dense and complete monitoring system of sediment, how long it takes to achieve a good state of monitoring system, for example, in Brazil. I know, supposing a steady resource campaign and a political decision to establish such kind of system.
How long to establish a network?
Yeah.
Wow. It's a very tricky question, right? Well, at least I would say at least, and the minimum, I would use at least 2 hydrological years measuring in the whole year.
Okay.
Okay, for sediment, wherever technology or you use mechanical meters or the others. If you use others, I would say you have to measure more. As I said in the beginning of the presentation, we have a very lack of measurements. It's not only in Brazil. I can see this in other countries that I visit. I went to Laos for a program there to consulting in 2018, and they were establishing a dam in the Mekong River, and the data they are using, look at that, the data are using for establish the dam was about a station they have a 250 kilometer upstream.
Yeah,
They never measure. Not. I'm not talking about sediment only. Discharge.
Yeah.
And when we arrived there, we knew that they already had lost a dam in one of the tributaries of the Mekong River because of this. So that's not only our problem. There are these countries that we see that they are not measuring, and there is a wrong concept that we can translate data from a very far upstream to a place, and I know we can use this when we don't have, but this is not very comfortable. That's not a good data to at least to establish a dam. I can tell you about one bad experience we have here in Iguaçu River. In 1992, I measured a very high flood in Iguaçu River, Iguaçu River, the mean discharge is about 1,100 cubic meters per second. And we measure about 30,000 cubic meters per second in 1992. And we measure with mechanical meters. At that time, we didn't have ADCPs. When we measured that, I thought that I never will saw again such a flood. But in 2010, we have a flood bigger than this, 10% bigger than this. But they were constructing a dam just in Iguaçu. And guess what? They constructed them in the protection, the protection of the place, the construction place, the dam, earth-fill dam, the construction below the level we found out in 1992. So what happened? They lost. The flood took all the equipment. They have a big loss, and the work was late by 2 or more years. I can't understand this. Maybe it's money. I don't know, because the loss what they have is much bigger than if they construct a protection with the last data we had. I don't know if I understand. We could talk this a lot, because we can see. I don't know in the other countries, but in Brazil, there are the people would like to go to the field. There is still a culture, the old culture, that the people goes to measure, that goes to the field, are people that doesn't have brain, that only have muscles to rise up and goes down with mechanical meters. And this culture is still going on here. So and the worst thing is that they think that they could establish some equations or things like this, that I can just transform this data from that to here, and that's okay. That's a problem. I think we're going to see disasters very soon because of this lack of studies, the lack of data they use for constructions in the whole of the world.
Well, Paulo, I want to thank you again for your presentation and your histories about measuring with these different techniques. Very impressive and many important material for the public. So thank you very much for your presentation. And I just want to remember to all the public that you can visit our webpage, Particles in the Americas. You can see all this lecture, including the lecture of Paulo Gamaro, to check fact and see the information again. Is completely available using our webpage. So thank you very much for attending this new season, and see you the next month. Thank you very much.
Well, it was my pleasure to be here. And I would like you to give the people, I forgot to put in the presentation my email. If they have questions, they could send to me. I'd like also to thank you, Pedoki, and Yogi, for this invitation. It was a pleasure to be here. It was a pleasure. Thank you. Thank you.
Bye-bye. Thank you.
Bye.
Los siguientes contenidos de Uninorteco te pueden interesar. No olvides suscribirte a nuestro canal.